Hello everyone and welcome back to this next lecture. So in the previous lecture I had described in brief what this course is about and the fact that we're using the Texas Instruments TMS 320 F28069 microcontroller. So in this course I'm going to talk about who is this course for, or who are the students who should be taking this course. And also I'll be answering another question as to why we are using C programming for programming the microcontroller in this course. So, to begin with, it is important to acknowledge that there are many ways to program a microcontroller, especially now in this day and age. 20 years back, we didn't really have that many options, and even when I was programming 10 or 15 years back, there weren't too many options. The more advanced graphical user interface based applications were proprietary and usually were quite expensive. Even to buy those specialized toolboxes, it was quite expensive and only a few R&D organizations could do so. But however, now almost every simulator offers graphical user interfaces. So for example, these graphical tools are sometimes available along with simulation software like Simulink or even with softwares like Plex and many others. So in these graphical tools, you can convert your control code, which you have developed using blocks, which are available in Simulink and other simulation softwares, directly into C programs. And these C programs in turn are compiled into assembly code, which is finally downloaded onto the microcontroller. All this is done automatically. You just have to click one button. When you've done simulating your system, when you are ready for actually implementing your control code, you just have to click one button and this will convert your control code into C code, which in turn will be compiled into assembly language code and finally downloaded onto the microcontroller. So therefore, you might ask, with all these kind of tools, why on earth would you be writing C programs, right? If you can just create your control code using these graphical user interfaces, using simple block sets, and even inbuilt blocks with Simulink. Like Simulink and many other simulation software have inbuilt blocks on PID controllers and many other controllers. So you can just use those and convert that into assembly language code. Why do you want to write a C program? So the question is this: is such a course of any value now that these graphical tools exist? And this question is what this course is about. At least this lecture, I'm going to try to answer this question. So, there are as I said, several graphical tools. Many are along with simulation softwares, many are separately purchased, and these are very, very popular in research and development. Many R&D organizations or even R&D wings of large organizations will use many of these graphical tools, right? They have licenses for the simulation softwares. They also have sometimes licenses for these add-on graphical tools. And when you're working in R&D, it is extremely useful to quickly validate your control techniques. The reason is, in R&D, the creation of advanced control techniques itself is very complicated. And therefore, as you are building your control loops, for example, a controller for something like a wind turbine may have multiple control loops. They may have several feedback loops, feed-forward loops, and many other loops. And therefore, it takes a long time to be able to synthesize these control loops and to be able to optimize them. And all the time you have to keep making changes to your control loops as you keep optimizing them and making them better and better. And if you have to now start writing C programs, each and every time you make a change in your control code, it can become very, very complex and cumbersome because now you have a double burden. Not only do you have to actually work on advanced control systems, but you also have to now fight to actually convert your control techniques into C programs or even worse into assembly language code. So this can significantly extend the length taken to complete advanced research projects. And in such a context, these graphical tools that are extremely useful because they cut down the amount of time that is needed. You can, if you're a researcher, you can design your control techniques either using these graphical tools or using any other software or you can use even a simpler language like Python and use some of the packages available with Python like NumPy or Pandas or even some AI based tools. And when you're ready to actually implement and test your control technique, all you need is one click. You just have to click on one button and automatically all your control code will be compiled and finally downloaded into assembly language. Right? So this is so very convenient because now you don't have to fight a double battle. Your battle is simply designing control algorithms. And nowadays, these tools support many microcontrollers. They're continuously adding newer and newer microcontrollers to their libraries. So they support larger and larger number of microcontrollers. So unless you're using something which is very new and very experimental, the chances are that you can use your graphical tools for your microcontroller that you are currently using in your hardware setup. So this will help to reduce the time spent on R&D projects. Now, the problem is this: to be able to work in R&D, one often needs advanced degrees, right? Most often you need a PhD, and sometimes even a master's will do, but quite often you need a PhD. Now, this is a problem because for those who are pursuing undergraduate degrees like a bachelor's in engineering or diplomas, depends on where you live, in which different parts of the world, there are different types of degrees. Some countries have only a bachelor, some countries even offer a diploma, and which is a slightly lower level degree. There are many. For those who are pursuing such degrees, the jobs that are available once you complete your degree is not in R&D, is most often as hardware engineer, firmware engineer, or test engineer. So even if you end up working in R&D, the chances are that you're not actually working on R&D projects. You are working as a hardware engineer, a firmware engineer, or a test engineer, and your job is to actually implement the final implementation of control code. And even in these domains, you will find the use of different graphical tools. For example, you may find the use of LabVIEW or many other automation software. But when you are implementing your final control code as a product code, right? If you're building a final product, let's say for example you're working in a company that builds uninterruptible power supplies, then the final product code for this uninterruptible power supply will be written in C programming, and sometimes some parts of it may even be written in assembly. Alright, so if you're looking for a job after your undergraduate degree or after your diploma, you will gain significantly if you have an in-depth knowledge of microcontroller architectures and programming. If you are only focused on those graphical tools, you may not be in a great position to get a job if you're only an undergraduate. Because remember, if you're only an undergraduate or if you're only completing an undergraduate degree, then they may expect you to work on the final implementation product and not on R&D projects. And therefore, you will need to learn C programming and you will need to know the actual architecture of the microcontroller and not just be able to convert the code from a graphical user interface into final assembly language code. So, and this is the reason this is important is that the power industry is growing rapidly. There are, number one, jobs in large companies. There are a large number of startups. There are a large number of mid-sized companies. And with all these companies, there are a large number of firmware and hardware jobs that are available and will be available in the coming years. And these jobs are a very, very easy entry point into the industry, so that at least you get your foot into the power industry. And once you are into the power industry, you can then look for more lucrative jobs in the future, such as you can upgrade into R&D as time goes on. But as a junior engineer, if all you know are graphical tools, then you may not be in a good position to enter the hardware industry or enter the power industry as a firmware or hardware engineer. And therefore, this course is specifically meant for that. I have created this course for those who are seeking to enter the power industry or those who are going to move on to additional degrees such as doing a master's, where you would be expected to learn C programming and assembly language sometimes, or even microcontroller architecture. Because if you have a job, if you get a job as a teaching assistant or a research assistant, you would be expected to know how to program a microcontroller with C programming and not just with graphical tools. So this is the reason why this course is focusing completely on C programming and also on how to understand the architecture of a microcontroller so as to make your C programs more effective. So I hope this lecture answered the question as to why we are using C programming and why not use any of those graphical tools, which are so much easier rather than writing C programs and understanding how a microcontroller works. But this course is to make young engineers ready for jobs in the power industry and also for helping you to get started with your further studies if you're going in for graduate programs like a master's. So, I hope this lecture was useful. If you have any further questions, please do post in the Q&A forum and I'll be happy to help you out. Otherwise, I will see you in the next lecture where I will talk about the requirements for this course. Thank you so much for listening and goodbye for now.